Physics lies at the heart of many games, like Portal, or even Angry Birds. Angry Birds is just trajectories of particles with a constant initial velocity in a gravitational field. You don't think of that when you play it, but that's exactly what you would calculate in your first year course doing a physics degree, is exactly what's going on in the game engine of Angry Birds. And this is actually a screenshot from something called Quantum Cats, which is kind of a quantum Angry Birds, which you can check out if you want. Yeah, this means that with quantum computers we could allow for games based on quantum physics. So currently there are already games that are based on quantum physics, but they take some small, easily simulable part of quantum physics. But with the ability to simulate large-scale quantum systems, it will open us to lots of new game mechanics that we might want to try out. Another thing is that we could use them for graphics. So searching databases is a significant part of rendering graphics. And so exactly like looking up, you need to know who has a specific phone number. You need to do problems like that when you're rendering graphics. And because quantum algorithms can do that faster, then this could be an important part of rendering graphics. There's also other ways that we could try, because rendering graphics is quite a large set of computational problems, so there are other ways that we can pick out things from the quantum algorithm zoo, which is this list of all the known quantum algorithms, and try and see how to work them into our algorithms for rendering graphics. So there's a few papers by a professor called Simona Karaman, I think. And there's also a recent startup called Boxcat, whose URL is Boxcat, but with a dot between the C and the A, as if it's an Austrian URL. So these are people that have looked at this problem. Now, I'm not really familiar with that so much because this is not something that people have really looked at too much. It's not something that's really been the focus of research into quantum algorithms. But if you want to see examples, then there are a few at least that I can point you towards. But one thing I would say about both of those things, about using quantum physics to generate your game mechanic and using quantum physics to render your graphics, is that what they will require is the quantum computing to be within the game loop. So within this constant loop of getting user feedback, you would get some user feedback and you would use that to formulate a new job for your quantum computer, and then the results from that you would give back to the player and so on. So that means that if your PC could have a quantum card that it slots in next to the graphics card, then fair enough. That would be feasible. However, quantum computer hardware is not going to be like this. So for example, at IBM hardware, this is a lab in which a few devices exist. So I think you can see about 2 devices in there, and this does not look like 2 graphics cards, as you can see. It looks like a whole room, and it's got people in and a lot of wires. So basically, the techniques that we use to reduce noise are very big and expensive. So for example, you have to cool the devices to almost absolute zero, and you need quite a large device to get those sorts of temperatures. So the current model is of a cloud-based service, and of course we do have games which operate over the cloud. So for example, massively multiplier games do have to rely on the cloud within the game loop. So we could imagine one day there'll be enough quantum devices that we can indeed use some time on those devices, incorporate it into quantum computing into the game loop. However, in the near future, where demand will outstrip supply, if you want to have a game that's got 1 million players, there are not 1 million devices to run it on, even if they're each using one, and the time it takes to send a job is not the kind of time scale that you would want if you're rendering graphics. So in the short term, it's best to consider quantum computing not inside the game loop. We have to move it out of the game loop and then find applications for it elsewhere. So for example, if you're using quantum computing for optimization, then you can generate a bunch of puzzles and work out what the best solution is and work out how to give feedback to the player. For example, in our traveling salesman problem, you can generate a load of traveling salesman problems. You can use the quantum computer to work out the optimal solution. You can then bake that optimal solution into your game and then ship it. And then the quantum computing happened in the design stage. It doesn't happen while the game is running. Or you can have it during a loading screen, so you could procedurally generate a new puzzle, and then while you're loading, you're using the quantum computer to work out the best solution for that. But you're not having it within the game loop. So similarly, you can easily determine whether a random level that you've generated is possible to beat. So if you're randomly generating one of these Zelda puzzles, you can maybe run it on a quantum computer to see if that level is beatable, and if it is, you know you can give it to the player and you're not giving them something impossible to do. And of course, this is a problem in procedural generation at the moment. You can randomly generate content. You need it to be beatable, and so often what this means is that there are limitations to how the randomly generated content is made to ensure that it can be beaten. But this sort of cripples your ability to do random generation in a scale, in a way that is as flexible as you might want. So it'll just increase your ability to find new ways of randomly generating levels, because you will increase your ability to be able to do this verification step of working out whether you can actually beat the level or not. So in this case, the quantum computing is used maybe in the design stage or during a loading screen, and therefore is not intrinsically in the game loop. It's somewhere that the player is happy to wait for a little while. And also you can produce truly random numbers more easily. It removes the need to rely on pseudo-random numbers. So this is something where you can pull a bunch of random numbers out of the quantum computer during a loading screen and then use it in the next level, depending on what your application is. Another thing, so when I talk to game developers about quantum computing, one thing they often want to know about is graphics. So I've talked about graphics a little bit, and as I said, it's not something that has been actively developed. So there's room for more work to be done on how you can use graphics, but it's probably not something you're going to do in the next few years on a quantum computer. Well, at least not within a game where it has to be in the game loop. Pre-rendered graphics might be a completely different thing. Another thing that people are quite interested about is quantum computing for AI. So AI for quantum computing is also something that is an active area of research at the moment. So people are doing some interesting things in this. And you could use a quantum computer for enhanced AI during your game. And then this isn't necessarily in the game loop either, because it might be during your wait for another turn. I play a lot of Civ 6 at the moment, and I'm used to having to wait for a little while in the middle of my game because the other players are having a turn. So this is somewhere you could also use quantum computing. Pertaining to AI, someone asked basically if we could make brains in a quantum computer that have true emotions or feelings. And well, in theory it's possible. So if you ask me the same question about something of a similar size and complexity to a brain, such as a bowl of soup, and there's crazy weird stuff going on in the bowl of soup as well. Turbulence is a very tricky problem. So in theory, you could, a bowl of soup is just a quantum system, and you could simulate that quantum system on a quantum computer. Or if you ask me about a piece of cheese or whatever, I would say, yeah, sure, you can do that. But a brain, well, there are philosophical implications to that I don't want to get into. So I guess so, but yeah. That would also require a very large quantum computer. So let's go more for a quantum version of Watson beating Jeopardy rather than trying to come up with Lieutenant Commander data for now. Okay, so this was the first part, what quantum computing might do in the long term. So inside the game loop, we might use it for quantum physics simulations and for graphics rendering. But in the shorter term, so it's still in the medium to long term, outside the game loop, we can use it for optimization-based tasks, procedural generation, AI. We can also use it, I didn't have a slide on this, but we could also use it for developing new game mechanics, where we use the quantum computer to prototype out the game mechanic, but then find a way to do it more efficiently, such that it can just run on a normal computer and doesn't actually need to rely on the quantum computer. So you use your simulation to prototype a new type of game, but then you take the basic essence of that, because when you're making a game, basically you want it to be fun for the user. You don't necessarily have to have it purely scientifically accurate. So you can abstract out what is fun about that game, what is engaging about that game, and then re-implement it in a way that's more efficient.